let's begin. Last time we considered induction for natural numbers, and we introduced three forms thereof. The first was the mathematical induction principle that says that for each property phi of natural numbers, if phi holds for 0, and for every natural number n, if phi of n holds, then phi of n plus 1 holds as well. So it seems we have a comment. I cannot hear anything. I see. Some of you can't hear me, but probably not everybody. So anyway, you will have a record of the lecture, so it is not that bad, even if you have some temporary technical problems now. So I think that that we may continue. If this two holds, that is, if 0 satisfies phi, and phi is closed under increment, closed under adding 1 to the number. So if it holds for n, it still holds for n plus 1, then that means that phi holds for every natural number. This was our first form of induction principle, and the second form was the least number principle, which says that for each phi, if there exists a number that satisfies phi, then there exists the least such number m, so that phi of m, but for every lesser number, phi fails. And the last form, strong induction principle, this form was a little bit tricky. It says that for each phi, if phi is progressive, then every natural number satisfies phi. But what does it mean that phi is progressive? Progressiveness means that for every n, if all lesser numbers satisfy phi, then n itself satisfies phi as well. So it is enough. And we started proving the following theorem. The principles or statements. First, SIP, strong induction principle. Second, LNP. And third, MIP are pairwise equivalent or mutually equivalent. Every two of these are logically equivalent. Last time, we already proved that the strong induction principle is enough for the least number principle, and that the least number principle is enough for the mathematical induction principle. It remains to prove that 3 is enough for 1. So if I'm given with the mathematical induction principle, I may derive the strong induction principle. Let's prove it and thus finish this abstract proof. Okay. When proving this implication, we are given with the mathematical induction principle, of course, which says, let's repeat that for each property, let's rename it to psi, for the name doesn't matter. For every property psi, if psi holds for 0 and psi is closed under increment, if these two are true, then every natural number satisfies psi. So this is given. What do I need? I need my strong induction principle, that is, for every phi, if phi is progressive, then every natural number satisfies phi. I need to prove an implication under a universal quantifier. How is it possible to do that? In fact, there is a standard technique here. We say that let's consider an arbitrary phi, and let's assume that it is indeed progressive. Then let's try to prove that every natural number satisfies phi. So that means that I may expand my given statement list with progressiveness of some phi. Phi is also given. No, of course, that's given that phi is some statement. It's not given that phi is true somewhere. So I'm given with this object, two statements and some arbitrary phi, and arbitrary phi, and then I need to prove that every n satisfies phi. Okay, let's do that. It is a little bit tricky. Why? According to MIP, I need these two assumptions in order to conclude that some psi is true for every natural number. But phi is just progressive. It is not that clear that phi is that phi satisfies these two properties. In fact, we have proved that every progressive property holds for 0. But what about this one? It is not that clear. So instead of phi, we want to consider some other property. Let's do that. So we want to consider phi, not phi, but psi of n, which is the following. For every m which is less than n, phi holds. So psi says that phi holds for every lesser number. Is it clear? If proof, this proof is which page of lecture note? Okay, this is page 24. And it is called theorem 4.5. Okay, if you want to track our progress via the lecture notes, so let's consider this property. And I want to prove that this psi indeed is true for 0 and is closed on the increment. Okay. Statement 1. I say that this one is true for 0. Why? Indeed, psi of 0 is the following statement. For every m which is less than 0, I mean just natural numbers. So there is no natural number which is less than 0. For every natural which is less than 0, phi of m holds. What does it mean? That means that for every natural number, if it is less than 0, then phi holds. Is it true or false? Or does it depend on phi? So, gentlemen, what do you think?
It's true.
It is true. Why?
The assumption is false.
Of course. This assumption is false. For every natural number, for whatever natural m, the assumption is false. Hence, the whole implication is true. That means that our psi of 0 indeed holds. It's a little bit trickier with the second statement, where I want to prove that for every natural number n, if psi of n holds, then psi of n plus 1 holds as well. Here again, I have an implication under a universal quantifier. How am I supposed to prove it? Assume that n is indeed some natural number and psi of n holds. I need then that psi of n plus 1 holds as well. But what does it mean, psi of n? It is just the following. For every m which is less than n, phi holds. And what do I need? For every m which is less than n plus 1, phi holds. So I need to get the following fact. If phi holds for every number less than n, if it holds for every number less than n, I want to derive from that it holds for every natural number less than n plus 1. But which numbers are less than n plus 1? So let's consider an arbitrary m, which is indeed less than n plus 1. Then I have two cases. You know, every nature which is less than n plus 1 is either less than n. It is the first case. And the second one is as follows. Then m equals n. Is it clear that m is less than n plus 1 if and only if it is less than n or equals n?
Clear, yes.
Of course. So
Yeah.
let's see these two cases. Remember that we need phi of m. Now we have considered an arbitrary m less than n plus 1, and we need phi of m. Why is it true? In the first case, we know that every m which is less than n satisfies phi. So in the first case, it is quite clear that phi of m holds. And what can one say about the second case? Let's look at this statement and compare it with the statement of progressiveness of phi. We know that phi is progressive. And being progressive means what? We know that phi is progressive. That is, for each n, if every lesser number satisfies phi, then n itself satisfies phi. And here we have exactly the assumption of this implication. So phi of n indeed holds. So we have phi of n and phi of m as in this case m equals n. So in both the possible cases, I have proved that phi is true for m. Phi of m holds for every m which is less than n plus 1. That means that psi of n plus 1 holds. So now, do you have any questions concerning this part?
No.
No questions, but anyway, I hope that it is quite clear. So,
Sorry.
So
Is
please.
it possible to quickly review it? Because
of course.
one part wasn't clear for me. Thank you.
To review what? Statement 2 and its proof?
Yes, the statement 2. Yeah.
Statement 2, of course. I need to prove that for every n, if psi of n, then psi of n plus 1. But what is psi? Psi says exactly the following. Every number which is less than n, for every number which is less than n, phi of k is true. So, I want to prove this implication. I'm going to apply the standard technique. Assume that we are given with some n, and psi of n is indeed true. For otherwise, if psi of n is false, then an implication with a false assumption, of course, it's true. So it's not worth considering. So we assume that psi of n is true. But what is psi of n? Psi of n means that every number which is less than n satisfies phi. And what do I need? I need to prove that every number which is less than n plus 1 satisfies the same phi. But let's consider some arbitrary number which is indeed less than n plus 1. Every such number is either less than n or equals n. If my m is less than n, then I have already assumed that it satisfies phi. So in this case, in the first case, I obtain that m satisfies phi indeed, which I need. And what if m equals n? So this time I need phi of n. How is it possible to get it? I know that phi is progressive. Why do I know that? Because this was one of my assumptions. I need to prove that every progressive property phi holds for every natural number. So I have assumed that phi is indeed progressive. As it is progressive, that means that if all numbers less than n satisfy phi, then phi is true for n as well. But now I am given that every number less than n satisfies phi. Hence, n satisfies phi as well, due to this progressivity assumption. So phi of n, and now every number less than n satisfies phi, n satisfies phi, hence every number which is less than n plus 1 satisfies phi.
Yes, thank you.
So hopefully it has become more clear.
Yes, thank you very much.
Okay. And now let's look at the bigger picture. Now I have proved that psi holds for 0 and psi is closed under increment, under adding 1. But I know from MIP that every such property is true for every natural number. So, applying the mathematical induction principle, I can conclude that every natural number satisfies psi. But what do I need? Eventually, I need that every natural number satisfies phi, not psi. But what is psi? Psi means that psi of n means that every number which is less than n satisfies phi. So I have such a strange property. For every n, if m is less than n, then phi of m. How is it possible to conclude that every natural number satisfies phi? Okay, statement 3. Every natural number, let's rename it, every natural number k satisfies phi. That's easy. Let's consider an arbitrary k. So let's take k plus 1 for n. From this one, I know that for every m, which is less than my n, that is k plus 1, phi of m holds. But clearly k is less than k plus 1. So if I take k as m, I will obtain phi of k, which is the thing I need. Is it clear?
When we took phi m equals k, the property hold as m is progressive, right?
Phi, and
No.
we so
The last
I
one.
want to. So in general, I need to prove that if phi is progressive, then it holds for every natural number. Here, in this statement 3, I don't use progressiveness. Why? I have already proved that psi of n holds. And now I unfold the definition of psi. Psi is just for each m less than n, phi of m. So you may safely replace. What was your questions?
I got it. Thank you.
Okay. So phi holds for every number, which is the thing I need. Every progressive property is true for every natural number whenever the mathematical induction principle is given. So that means that we have 3 implications from 1 to 2, from 2 to 3, and from 3 to 1. Of course, these 3 implications mean that every 2 statements out of these 3 are equivalent. What does it mean in general? That means that whatever principle you take, it might be called the axiom of induction. Is it clear? Of course, it was abstract. It was abstract, surely. But dear students, mathematics is an abstract science. Unfortunately or fortunately, but it is so. Earlier, I planned that we proceeded to graphs directly from this point, but later I thought that we needed some practice, some crash course in set theory. So let's learn some basic things about sets. Okay, our new topic is sets. By the way, dear students, what do you think? First of all, have you heard this word set in mathematical context?
Yes.
Yes.
Definitely you have. But what is set in your opinion?
A group of objects.
Group of objects. So group of objects. So what else? Any other ideas? What is set? Or everyone is satisfied with this description? Apparently, everyone does. So,
Excuse me, does the set cares about repetitivity or not?
repetitive entities, no, they are not allowed in sets. In a set, every object is either a member or not. And if you have multiple counts of some object, you need some other formalism. In general, sets with repetitive objects are called multi-sets, and the main idea is that they might be modeled. They might be modeled in set formalism. So we don't need them in mathematical, we don't need them as a primary notion, as a primitive notion. So we may model them. Dear students, one of the most basic ideas of mathematics is to be content with some, with very humble set of primitive objects and construct everything you need from them. So in mathematics, typically you have few axioms and derive from them a multitude of theorems. But now we face a very specific problem. What is the object of mathematics? In general, they tend to think that the object of mathematics is comprised of numbers, figures of plane or bodies in space or something like that. But do we have a unified object of mathematics? That's the question. You say that set is a group of objects, but may one think that this is a definition? Is it a definition? What do you think? It's a philosophical question, but anyway, please don't hesitate to share your thoughts. Is it a definition?
No.
No, but why? What's the problem?
It didn't contain all of the properties.
One may say something like that. Here, set is to be defined. But what is a group? And what is an object? We see no definition for group and no definition for object. Of course, you may say that these notions are intuitively clear. But are they? Are they? If set is supposed to be that fundamental for mathematics as it is it possible to define it in such unclear terms, a group? By the way, the word set is not worse than the word group. So why you define set via group and not vice versa? You may say that a group is a set of objects. So it's not a definition. It is just intuition. Is it possible to define a set? In fact, it is not possible. Why? Because every notion is defined from some notions which were defined previously. And if set is supposed to be the primitive, the most basic, notion of mathematics. Of course, it's not possible to define it from any other. So we have no definition for set. But what should we do? But there are rules. There are some rules which are called axioms in mathematical usage, axioms. Rules on how sets behave and how sets do behave. Do you know the game of chess or any other game of that kind?
Yeah. Yes.
What makes a piece say a bishop? Why is it a bishop or a king? Why is it a king? Because only because it plays some role according to the rules. So it is allowed to make such and such moves. One set of moves for a bishop and another one for a king or for a queen and so on. But it doesn't matter what is a king. It doesn't matter whether it is made of wood or of ivory or of metal or just some or it is only an imaginary thing, something like if you play chess with a computer, there is no physical object corresponding to the pieces. So likewise, we don't want to and in fact can't define set, but we want just to describe what's possible to do with sets. How should they behave? We will take some intuition, which gives rise, of course, from this idea, a group of objects, a group of physical objects, or something like that. And then we develop our rules from that intuition. But of course, our rules don't correspond to our intuition precisely. There are some difference. Okay, what can one say about sets? If you wish to model the whole mathematics in set theory context, you have to assume that everything is a set. Everything is a set. Every number is a set. Every figure of the plane or whatever is a set. Everything is a set. Of course, it's not axiom, strictly speaking. It's a philosophical postulate, which means that we just don't want to consider any objects besides sets. So, every number, every point, whatever it can mean, every function, every object of our mathematical discourse is a set. This is our first, I'd say, meta principle, our outer principle, which frames the whole universe of our discourse. Okay, everything is a set. One set may be an element of another one. One set may be an element of another one. What does it mean? What does it mean to be an element? Of course, it corresponds to our natural intuition that an object belongs to a group. Say you, as a student, belong to the group of MIPT students. Do you agree?
Yes.
Or as a human, you belong to the humankind.
Of course.
Of course. And so on. As a citizen of your country, you belong to the set of your country nationals. And so on. So this is our basic intuition. And in mathematics, we introduce a special symbol like this one. A is an element of B. So we read it the following way. The set A, capital A, of course, is an element of the set B. Or another reading, A belongs to B. Can I define this relation between sets? No, I can't define it. But I need to impose some rules for this thing. How is it possible for this thing to behave? Which rules? For example, I like the following rule. No A is an element of itself. No A is the following of is an element of itself. What do you think about it? Is it intuitive or not? By the way, dear students, what does it mean? This symbol. What does this symbol mean? It means that it is not the case that X belongs to Y. Is it clear?
Yes.
Okay, dear students, is it intuitive or not?
I think so.
So what? Intuitive?
Intuitive, yes.
Of course. Why? Because if you are a student, you can't be a member of a student. No group of students is a member of a group. And so on. So it's not possible that a group belongs to itself. It is a part of itself, but not a member of itself. It is a basic idea. And also this one. For no A and no B, I have that A is an element of B and B is an element of A. What about this one? Is it possible that A is a member of B while B is a member of A? If sets are groups or say boxes, is it possible that one box is contained in another box, but the larger box is contained in B? Is it possible? Intuitively. No, intuitively it's not possible. So of course, if I add some more sets here, it is still bad. So there is a general rule from which all this follow. This rule is called the axiom of foundation. The axiom of foundation. There is no infinite strictly decreasing sequence of the form. Of course, it's possible to avoid using words infinite and strictly decreasing and sequence in this statement, but let's give a more intuitive form of that. So it's not possible to have the following sequence of sets, where x1 is an element of x0, x2 is an element of x1, x3 is an element of x1, and so on infinitely. It's not possible to have such a sequence. Is the statement clear?
Yes.
Do you have any questions? So, supposedly it's clear. Why these principles follow from this one? This quite easy to grasp. As a corollary, for example, I can say that there is no A, so that A is an element of A. Let's prove it. Assume otherwise. Then I have that A is an element of A, but also A is an element of A, and A is an element of A, and so on. So if I take A as x0, x1, x2, and x3, and so on, I will obtain an infinite decreasing chain. Is it clear?
Yeah.
Sorry, but I didn't get it. Like, because for instance, natural numbers, you can always find bigger one, which is. I didn't get the idea here.
So it is not possible to construct an infinite chain of sets, which so that every next set is an element of the previous one. Maybe you are thinking about something like that. Let's consider a segment from 0 to 1. This segment has this segment from 0 to 1 over 2 as a subset, and so on. But here we have not elementhood, not belong, but is a subset. These are not the same. It's not possible to have an infinite sequence of sets where every next set is an element of the previous one. So, is it better now?
Yes, of course.
So, something is not allowed. But what is allowed? Let's see. First of all, First of all, let's define this relation, that is being a subset. Now we may define it. Do you remember our first practice with predicates, where we said that, say, every rose is red? Do you remember it? For every x, if x is a rose, then x is red. Do you remember it from the first our lectures?
Yes.
Yes.
Yes, yes.
Of course. But what does it mean? One may render it the following way. The set of roses, is a subset of the set of red things. Do you agree? Every rose is a red. So every so the set of roses is a subset of the set of red things.
It's right.
So let's define this symbol exactly this way. We define that A is a subset of B. A is a subset of B, or another reading, A is included to or into B, or another way, B is a superset of A. What does it mean? That means that for every x, if it belongs to A, then it belongs to B. So this is our first definition in set theory, our first formal definition. A is a subset of B if and only if every element of A is also an element of B. So that means that the set of roses is a subset of the set of red things, according to our understanding. And this humble definition, by the way, allows us to prove something. For every three sets A, B, and C, I have the following. A is a subset of A. Is it intuitive or not?
Yes, it is.
Dear students, just see, A is the subset of A, but we have, in the above, we have explicitly forbidden A to be an element of A. So A is a subset, but it is not possible for A to be an element. So to be a subset and to be an element are not the same. They are distinct relations, and it is one of the main distinctions of set theory. To be an element is some primitive notion. You are either a member of some group or not. And to be a subset is some other thing. That means that every member of one group is a member of another group. We don't say that the group A as a whole belongs to some set. No. We just say something about its members. One of the basic distinctions of the set theory is that a group is something other than its members. It is one of the main ideas. Of course, for example, if you have an academical group of students, of course, this group itself is not a student. Do you agree?
Yes.
In plain words, a set is some new thing comparing to its members. Say 2 is a number, 3 is a number, but if we group them together, it is not a number. Say at least not the same number, not 2 and not 3. By the way, as a degenerate, as a borderline case, I may group an object just with itself, and then still I shall obtain a new thing which is not the same as my object. Is this idea clear? We shall come back to it. We shall come back to it later. Okay. A is a subset of A. If A is a subset of B, and B is a subset of C, then what?
A is a subset of C.
Of course.
A is a subset. Yes.
And the third one? The third one needs another definition. So we have that. Okay, let's postpone it. Okay. How is it possible to prove these things formally? It is not hard indeed. Why, for example, A is a subset of A? A is a subset of A. That means that for every X, by definition, if X belongs to A, then X belongs to A. But this implication is always true. Why? Why is it always true? Because if X indeed belongs to A, you know, the conclusion is true, hence the implication is true. If X does not belong to A, then the assumption is false, hence the implication still true. Clearly, this implication, you may make a table and see that it is always true. It's always true. So this one is always true. And here we have that, we have what? That for each X, this one is true. And this one is true as well. From these two, I may prove that if X indeed belongs to A, then what? Then X belongs to B. Hence, from the second one, I may obtain that X belongs to C. So these results are based on our simple logic, our properties of implication and conjunction. Is it clear?
Yes, but I have a question.
So please.
Yes, the symbol of the subset, right? If we don't write it with the line under it, it means
so what about this symbol?
Yeah, it means A cannot be a subset of A, right?
In general, this symbol is used for both the same as this one and for the following. A is a subset of B, but A is not equal to B. So there is some ambiguity with it. So I don't like this symbol. But in practice, they use it in two meanings. Either in this one, so every element of A is an element of B, and maybe converse. Maybe the converse. It might be that every element of B is an element of A. Or otherwise, they use this symbol for the following: A is a subset of B, but these two sets are not equal. Is it clear?
Yes. It is.
I just don't like this symbol. You may use it if you wish, but of course make it clear what does it mean. The same as this one, or the fact that A is a so-called proper subset. So A is a subset, but not the same as B.
When it doesn't have equal, it means the set, for example, B is larger than set A, right? Always.
What does it mean? Equal.
It means all of the elements of set A are equal to maybe
No. What does it mean that all elements are equal to all elements? So if you take one element of the first, it should equal every element of the second. Of course, not that. Let's define that two sets are equal. Let's define it. By definition, that means that every element of X of A is an element of B, and vice versa. Every element of B is an element of A. Do you remember the meaning of this symbol?
Yes.
Equivalent.
Of course, logical equivalence. That means that both sides are true or both sides are false. So this is just two implications. So this is equivalent to the following fact. If X is an element of A, then X is an element of B, and vice versa. If X is an element of B, then X is an element of A. Two implications. So clearly, A equals B if and only if A is a subset of B and what?
B is a subset of A.
Of course. So we may state our lemma too. First of all, A equals B if and only if B is a subset of A and A is a subset of B. So they usually use so-called Euler's diagrams in order to depict sets. So what does it mean that A is a subset of B, diagram-wise? That means that A is a part of B. So A consists of only such elements which are elements of B. And what does it mean that they are equal? They are equal, that means that A is an inner part of B and B is an inner part of A. That means that they are the same. That means that they are the same. Of course, it is hard to depict it in any meaningful way. So,
Excuse me. For defining or writing the graph of the A is element of B without equal, is it possible to draw it or draw the graph? Or it's not possible?
To draw a graph, you mean such a diagram?
Yes, sorry.
So you want to draw what? You may try and share your screen for us.
No, I want to know if it's possible to draw A is a subset of B without equal, without the line of
I see your point. How is it possible to draw such a situation? You may, for example, explicitly provide a point, an element, which belongs to B but not to A. Say if here you have some x0, it is an element of B but not an element of A. But dear students, please use these diagrams in moderation. Diagrams prove nothing. They are not proofs, and they are they are not too sophisticated tools in depicting relations between sets. So please, in fact, avoid using them. By the way, we have a question here. Is it possible to consider the set of all sets? No, it's not possible. Why? Because this concept is logically contradictive. It is even contradictive if we don't assume the axiom of foundation. But using the axiom of foundation, it's obvious that there is no set of all sets. So, as a corollary, we may obtain the following fact from the axiom of foundation. There is no set of all sets. What is the set of all sets? Clearly, if V is a set of all sets, it's a good question. Then V is a set, is an element of this set. But we have already proved that from the axiom of foundation, it's not possible to have a set which is a member of itself, which is an element of itself. So that's a contradiction. By the way, even without this axiom, it's possible to prove that the set of all sets is impossible from other principles. Okay, but let me continue with the properties of set equality. We say that A is equal to B if and only if one is a subset of the other one and vice versa. Also, equality is reflexive, that is, every set is equal to itself. Equality is symmetric, as our intuition goes. If A equals to B, then B equals to A. And also, equality is transitive. If A equals B and B equals A, it should be that A equals C. How is it possible to prove these properties? You may consider the definition, but there is a better way. You may use our lemma 1. But how? Let's see, for example, how is it possible to prove the third statement. Assume that A equals B. Then, by our first statement, we have that A is a subset of B and B is a subset of A. Using logic, we may obtain from that B is a subset of A and A is a subset of B. But this is, according to the first statement, means that B equals A. Any questions, please? So, we have such properties of equality. But that's not all. That's not all. By the way, you know that by definition, two sets are equal if and only if their elements are the same. That means that every element of A belongs to B, and every element of B belongs to A. That doesn't mean, of course, that every element of A equals any element of B. Of course not. That means that every element of A belongs to B. Every element of A belongs to B. Okay. But dear students, another interesting question. What do you think about the following? Say C is an element of A and A equals B. Is it enough to say that C is an element of B?
Yes.
Of course. Why? Because according to our definition, equality means that the elements of the sets are the same. So, yes, that's it. But what about this one? Assume that A equals B, and A is an element of C. Then B is an element of C as well. What do you think about this one? Can you prove it somehow?
Using lemma 1?
Using lemma 1. But lemma 1 is about inclusion. And here we have elementhood. We have elementhood. Clearly, of course, you are right. If A is a subset of C and A equals B, of course, from our lemmas 2 and 1, it follows that B is a subset of C, of course. But it is not about subsets. It is about elements. In fact, there is no way to prove it from our definitions. But is it intuitive? We want, do we want that equal sets behave exactly the same way? Do we want equal sets behave exactly the same way? If one is an element of whatever set, then the other one is an element of the same set. Is it natural to assume it?
Yes.
Yes. And
Yes.
intuitively, that should be true, but we can't just prove it. So if we can't prove it, but we want it, we must postulate it. Take it as an axiom. And indeed, this one might be taken as the axiom of equality. The axiom of equality. That means that if A equals B and A is an element of some C, it should be an element of B, should be an element of C as well. By the way, if I group these two together, I see that A and B, if they are equal, behave the same way on both sides of the symbol, either on the left or on the right. Is it clear?
Yeah.
So from this one, I may obtain the following theorem, which I'll call the substitution principle. I don't want to prove it, for it would require some analysis of what a property is, some meta-analysis, which is not among our goals now. So the substitution principle, for every property or predicate for every predicate phi of x, which is defined just in terms of elementhood relation, but in set theory, everything is defined in terms of this relation. For every such predicate, if A equals B, then phi of A takes place if and only if phi of B holds. So that means that equal sets behave identically. Exactly what our intuition says about equality. Equal sets behave identically in any situation. They behave identically everywhere. So I may freely substitute a set for an equal. Is it clear?
Yes.
Sorry. You wrote which is defined just in terms of what?
Of this symbol. This was comma. Of this symbol. Being an
Okay.
element of this symbol. Is it clear? So I may freely substitute a set for an equal set. So I hope it is clear enough. And now let's see how is it possible to construct new sets. So we just we have just seen that there is no set of all sets, but which sets indeed in fact exist. So set construction principles. Set construction.
Excuse me.
Uh-huh.
I cannot understand the sentence you wrote for every predicate phi x which is defined just in terms of that symbol. I can't understand it.
Okay. Now, for example, let's see what does it mean that A is a subset of B. That means that for each x, if x is an element of A, then x is an element of B. Which notions are used here? Which symbols, formally speaking? Logical symbols, and also this symbol of being an element. Do you agree?
Yes.
On the other hand, this is some predicate, some property of A and B. And this property was defined exactly in terms of just our elementhood relation and logic. But logic is by default, is accessible by default. We have logic. There were no other non-logical symbols here. This was defined just in terms of set inclusion.
Yes, I understood. I understood.
So
Thank you.
every such property, if in doubt, you may just take this part into brackets and forget about it for every predicate. For every predicate, they are mutually substitutable. You may substitute equal set for another set equal to it. Is it clear now?
Yes, it is. Yes.
So they behave the same way. This was my idea. And now set construction principles. Of course, formally we may construct all sets according to our rules. But this is too much for our particular course. In order to simplify things, we shall assume that some sets are already defined. Assume that the set of naturals is already defined. And also integers, rationals, reals. Let's take this simplifying assumption. And now set construction principles. Do you know the motto of the United States?
No.
In Latin it says, e pluribus unum. You may read it from their seal with the eagle. You know, they sing with the eagle. Here one reads the following caption. E pluribus unum, which in English means that out of many, one. So let's code name our set construction, our first set construction principle this way. What does it mean? Assume that you have some sets A1, AN. It is principle here that there are just finitely many of them. Let A1, AN be some sets. Then there exists a set this one such that for each x is an element of this set if and only if x either equals A1 or equals A2 and so on, or equals AN. So if I have some objects, some sets, finitely many of them, I may group them together. So informally, that is, I may group a few, that is finitely many, a few given sets together. It is not that easy with infinitely many sets, but for finitely many sets, I may easily group them together. For example, I may group together 2 and 3. You know, I have assumed that natural numbers have been already defined. I may group these two together. What are the elements of this set? X is an element of this set when? If and only if, so please continue.
X is equal to or 3.
Of course, that's it. And now, some of you had a question about multiple occurrences of an element in a set. Now let's prove that they are not possible. This set is equal to this one. So that means that neither occurrence count no order of mentioning our elements takes any role. So these notations are synonyms. They are synonyms. The proof is very easy. When X belongs to this set, we have already established that that's equivalent to this one. X is either 2 or 3. And when X belongs to this set, so please, by definition, that means that X
Either 3 or 2.
not that fast. X equals 3, or X equals 3, or X equals 2. This is exactly by our definition. Do you agree?
Yes.
Yeah.
But now let's look at these two disjunctions. From logic, it's clear that they are equivalent. If they are equivalent, so we see that every X belongs to this set if and only if it belongs to that one. So they are equivalent. Excuse me, they are equal. They are equal that every X is a member of the first one if and only if it is a member of the second one. Is it clear?
Yeah.
Yes.
It is.
In mathematics, please give me 3 more minutes. In mathematics, we like various borderline cases. What if here we have just one set? What if n equals 1? Then, what if n equals 1? Then my definition will give me the following. For each X, X is an element of this set, A in curly brackets, if and only if X equals A. What can you say about this set? It is called the singleton, from the word single, obviously. It's called the singleton of A. What does it mean? It is a set which consists of only one object, which is 2. Ha! So this is a group of one student. But still, this group is not a student. It is a group of one student, but it is not a student. Let's formally prove why is it so. Okay. What if in this formula, which is from our definition, by the way, this is an axiom, let and then, this is an axiom. What if we take A for X? Which statement should we obtain? A is an element of the singleton of A, if and only if A equals A. Is it true or false?
True.
Of course. Why? We have proved it in lemma 2. According to lemma 2, this one is true. And if it is true, then this should be true as well, as it is equivalent to a true thing. So I see that every set is an element of its singleton. Corollary. For no set, its singleton equals the set itself. Let's prove it. Of course, we know that A is an element from the contrary. Assume that A indeed equals its singleton. Then you know, A is an element of the singleton, while the singleton equals A. Ha! But two equal sets have exactly same elements. That is, A must be an element of A, which is not true according to the foundation axiom. It's not possible for a set to be an element of itself. So, no set equals its singleton. We have formally proved that under our assumptions, under our axioms, the group of one object is not the same as that object itself. Is it clear?
Yes.
So, A is not an element of, so A does not equal the singleton of A. In fact, it is quite hard to grasp intuitively. For example, if we consider plane and its points, we may easily obtain that every figure in our plane, let's by the way denoted by the Greek letter pi, every figure on our plane is a subset of the plane. Do you agree with such an interpretation?
Yes.
Every figure, say, a disc, a circle, a square, either with the interior or without, a triangle, I don't know. Every figure is a subset. But what can you say about 1 point? 1 point, x, is just a member of the plane, for the plane is a set of points. But what about this object, singleton of x? Singleton of x is a subset, but not an element in general. So you should have a distinction between a point and a 1 point figure. According to set theoretical formalism, these things must be distinct. And it is quite counterintuitive, by the way. But anyway, according to our axioms, which we have introduced so far, a group of one object and that object itself must be distinct things. Much like a group of two objects in general does not coincide with any of these objects. So, any questions, please?
Yes. Sorry for the picture you drew the plane. Could you please show it?
So?
And you defined the circle as F, and you said
No, F
F
is not a circle. F is this thing. It's not a circle.
F means everything?
Not everything, but some figure, some abstract figure.
So it is a set or it's an element?
It is a set, a subset of plane. Why? Because every figure consists of some points. Do you agree?
Yes.
And the plane is a set of all possible points. So every figure is a subset of points.
Thank you.
If you want to give a formal interpretation to geometry, to elementary geometry, if you want to interpret it in set theory, this is the most natural way. You say that the plane is a set and all figures are subsets. But the intuitive problem is with 1 point figure. What is it? As a point, it is an element. And as a figure, it is a subset. So you should make a distinction between 1 point and 1 point figure, which is counterintuitive, I agree. But it is necessary according to set theoretic formalism. Some general words of advice. Dear students, the main idea here is to a little bit suppress your intuition. You should play by rules with sets, by axioms and definitions. Please take these rules seriously and play accordingly. In many parts of mathematics, you won't have any useful intuition, at least at the first stages of your learning that branch of mathematics. So you have to play by the rules, by axioms and definitions. So, any more questions?
Excuse me. By the axiom of foundation, we say that there is no infinite elements in a set, right?
No. That means that there is no infinitely decreasing sequence.
Sequence.
You may have infinite elements, indeed. We see that there is a set of natural numbers. It is infinite. Do you agree?
Yes, this is my question exactly.
We have the singleton of natural numbers. Then see the following. Let's construct the following graph. In fact, membership is a graph. It's quite interesting. The set of natural numbers is an element of this singleton. 0 is a natural number, so it is an element of natural numbers. 1 is a natural number. 2 is a natural number. 3 is a natural number. So you have something like that as a graph. N, singleton, the singleton of n. And now 0, 1, 2, 3, 4, and so on. It is infinite. This graph is infinite. But the main idea with the foundation axiom is that in this tree-like structure, there is no infinite branches. Intuitively, there is no infinite branches.
And what does it mean? Infinite branches?
That means that it is not possible to descend infinitely by the according to the arrow. So have you got the idea of this graph? You may draw an arrow from element to a set. From an element to a set which this element belongs to. Probably that's not that clear, but anyway, you may have infinite elements, but it is not possible to infinitely take an element of an element, an element of an element, an element of an element, and so on. Is it clear?
It means we cannot have a set inside a set, or no?
You may have a set being an element of a set. By the way, we have assumed that everything is a set. So it's not a special category of things, an element. Every element is a set. But that means that this sequence must end. So it must lead us to an element with to a set without elements, we need another interesting concept, that of the empty set. The empty set, you know, at the empty set, the sequence necessarily breaks. For example, do you are you familiar with the symbol for the empty set?
Yes.
Yes.
We shall formally introduce it. We shall formally introduce it next time. But now let's use it informally. So every sequence, that means that every such sequence will lead us to the empty set at some finite stage. That's the idea. Taking an element of an element, an element of an element, an element of an element, you necessarily reach, you will necessarily reach the empty set. That's the idea.
Thank you. Thank you very much.
So if you have graphs of sets, here you have infinite branching. Infinite branching. What does it mean, infinite branching? That means that there are infinitely many arrows coming to n. But neither branch in this tree. Let's understand it intuitively at first. No branch is infinite itself. You may have infinitely many branches, but every branch is finite itself. Is it clear?
So we can have branches, but not infinitely, right?
Of course, you may have infinitely many branches, but no infinite branch. Every branch itself is finite.
Uh-huh.
That's the main idea here.
Mm-hmm. Yes. Thank you.
Okay. How is it possible to explain it intuitively? Assume that you are imagining, imagine the roads you may go during your life. Every such road is finite. Why? Because your life is finite. But in general, you have infinitely many directions you may go. Is it clear?
Yes.
In general, in this space. In this space, you have infinitely many directions. But during your life, you may go each one only for some finite distance only. So the same idea here. You may have infinite branching, but just finite branches. Any more questions?
Thank you very much.
Thank you, dear students. Thank you. I'll post the recording to YouTube soon. So I'm finishing.